All right. Okay, so in this video, we're going to look at compressible versus incompressible fluids, and I'd want you to be able to distinguish between them, not just know that most liquids are incompressible and most gases are compressible. I want you to also develop a deeper understanding of what that actually means. I said that the energy balances for compressible fluids look different than the energy balances for incompressible fluids, and I want you to know why in terms of math. But we haven't yet developed the energy balances. That will be in chapter 2, but I will show you the assumptions that we make when we look at the math between incompressible and compressible fluids. And so we're going to look at a quick example so that you would really understand what I mean in terms of being able to distinguish between them, because it's super important. So we're back to my board. So the incompressible, let's start with incompressible fluids, because this course is about sizing equipment for incompressible fluid, essentially liquids. And I would say incompressible fluids, liquids. And let's start by giving an example, because I think the best way to really understand something is by seeing an example. So an example of an incompressible fluid, let's say water. And let's assume that you are now using a pump to transport or transfer water from one location to another. So you have a pump and you have pipes connected to the pump. And essentially, we're not concerned with the pump right now. We are still in the introduction. We're going to be learning all about pumps later. But what I want you to know is that let's try to look and analyze what's happening here in the system. So the inlet or the suction side of the pump, I'll call it point 1, and the outlet of the pump where the discharge is, I'm going to call that point 2. And let's start with a very basic mass balance around this unit operation, whereby we know that the mass flow rate entering this pump is going to have to equal to the mass flow rate that exits the pump. Because we know that there is no accumulation of mass inside the pump. And we know from the law of conservation of mass that mass cannot be created nor destroyed. So essentially all the mass flow that enters into this pump is leaving. And in terms of math, this will look like this, m.1. And I say dot because dot shows that I'm talking about a mass flow rate. So it's kilograms per second or kilograms per hour. So you understand the point. Is equal to the mass flow rate leaving the pump, right? So I would assume everyone would agree to me on this. We also know that, and I'll call this equation A, we also know that density is mass over volume. And since we're talking about rates, I'll just say it's the mass flow rate over the mass flow rate of the liquid over the liquid's volumetric flow rate. So if I rearrange this equation, I will know that the mass flow rate is equal to the density of the fluid multiplied by its volumetric flow rate. So I can sub B into A to expand it. And if I do that, then I will have the density of the water at point 1, which is when it's entering the pump, multiplied by the volumetric flow rate of the water that's entering the pump, is going to have to equal to the density of the water at point 2, multiplied by the volumetric flow rate of the water at point 2. Now, since I'm trying to show you an example, let's actually put some numbers to it. Let's assume that at point 1, let's assume here that the temperature at point 1 is 20 degrees Celsius, and the pressure at point 1 is 1 atmospheres, which is just atmospheric pressure. So that is 101,325 pascals. So let me squish that here. And so the density of the water at 20 degrees Celsius and 101,325 pascals, you can look it up through Engineering Toolbox database, and that will be 998 kilograms per meters cubed. And let's assume at point 2, you have a higher temperature. So let's assume that the thermal inefficiency of the pump is really high, and for some reason, even though this is I'll just throw a crazy number, and I've never seen that before, but let's assume that the temperature doubles and goes up to, and I'm using crazy numbers just to send home a message, to really illustrate a point. So let's say that the temperature at point 2, where the water exits the discharge of the pump, is 40 degrees Celsius. Let's say that the pressure at point 2, let's assume that the pump doubles the pressure, or just about. So it's 200,000 pascals. And if we look at what the density of the water will be when it exits the pump, I looked it up at Engineering Toolbox. It is 992 kilograms per meters cubed. So folks, I want you to look at these two numbers. Realize how they are so close to each other. In fact, the difference is less than 0.5%, I would say. And so what we can do is we could simplify this equation by, if we assume that the densities are constant, then we could cancel them out if they're the same. And what we have left as a result is this equation. We have the volumetric flow rate entering the pump is going to equal to the volumetric flow rate exiting the pump. And we're going to call this equation C. And essentially, ladies and gentlemen, assuming that the fluid is incompressible allows us to reach to this conclusion. And this conclusion is very important because it helps us simplify the energy balance. And you will see that in chapter 2. But you see how beautiful this looks like right now? So for incompressible fluids, not only does the mass flow rate entering the pump is the same as the mass flow rate which exits the pump, and this is obvious, but also because the densities are the same and they're not very sensitive to the temperature and the pressure, at least for the operating range that we are identifying, then we also reach the conclusion that the volumetric flow rate entering the pump is equal to the volumetric flow rate exiting the pump. And so we could also use this to our advantage, knowing this. Now, when it comes to compressible fluids like gases, this is completely different. And I'll show you right now. It's a lot easier to see when there's a real example. So let's assume that we're talking about air, and similarly, we're looking at increasing the flow rate or moving air by increasing its pressure, let's say through a blower. And we are not really concerned about the blower itself. We are only concerned about trying to see what what assumptions we could make to simplify the mass balance, and if the volumetric flow rates entering and exiting the blower are the same or not. So let's assume the air that's entering the blower is at point 1, and the air at the discharge of the blower is at point 2. Similarly, we know from the conservation of mass that the mass flow rate of the air at point 1 has to equal to the mass flow rate of the air that's leaving the blower at point 2, and that's again because there is no mass accumulation in this blower. If mass happens to be accumulating in the blower, at some point the blower is going to explode. That doesn't make sense. And also we know mass cannot be created nor destroyed. So all that leads to this equation that whatever is going inside this black box has to leave. And also we know that the density, right, is mass over volume. And if we rewrite it differently, we know that the mass flow rate is equal to the density times the volumetric flow rate. And if we do the same thing, we sub B into A, sub it into the original equation, we're going to get to the same equation that we had. So the density of the air at point 1 multiplied by the volumetric flow rate of the air at point 1 is equal to the density of the air at point 2 multiplied by the volumetric flow rate of the air at point 2. Now let's pause here for a second and put some numbers so that we can see what's actually happening. And if we use these same numbers just for illustration purposes to see how the density changes, we could really understand whether or not we could simplify this equation any further. So let's assume that the temperature at point 1 is 20 degrees Celsius, and the pressure at point 1 is also atmospheric, which is 101,325 pascals. Now, if you look at an online calculator, the density of the air, you could also calculate it using, assuming ideal gas law, PV equals nRT. But for the sake of simplicity, you could also just look at online calculator. It will be around 1.2 kilograms per meters cubed. Now, at point 2, if we assume that the blower's thermal inefficiency is so high that it doubles the temperature of the air to 40 degrees Celsius, and the pressure that the air is discharged at is double the atmospheric pressure, so it's 200,000 pascals. And if you look at an online calculator as well, the density at point 2 is, ladies and gentlemen, 2.2 kilograms per meters cubed. You see how the densities now are so different. It's almost like we've doubled the density. And so this is important to make note of and understand that now, since the densities are not the same anymore, and in fact the differences between them are so huge, now it's almost double what it originally was. We can't really assume that the density stays constant, and if we can't do that, we cannot cancel out any terms, right? So the best that we can do is we could, if we wanted to evaluate the volumetric flow rate at the discharge or at the inlet, we have to take into consideration the changes in density. So if I was to write an equation, I would just say that the volumetric flow rate, I would say that the volumetric flow rate at the inlet of the blower is related to the volumetric flow rate at the outlet of the blower by the ratio of the densities from point 1 to point 2. So unfortunately, the densities do not cancel out. And because they do not cancel out, you have to consider the ratio of the densities, and therefore the volumetric flow rate of the gas that enters the blower is not going to equal the volumetric flow rate of the gas that leaves the blower if the temperature and the pressures are significantly different, as opposed to liquids or incompressible fluids. We've seen that the temperatures on the inlet and the discharge of the equipment has significantly changed, both in temperatures and pressures, and still the volumetric flow rate at the inlet and the outlet remain the same because the densities are insensitive to fluctuations in temperatures and pressures, so they get canceled out. And this assumption really helps us when we develop our energy balance equations, and it's going to simplify the energy balance so much so that it's going to be very easy for us to actually size pumps. And the energy balance that we develop to size pumps for liquid and incompressible fluids should not be used when we are trying to design equipment for compressible fluids. And that is because the volumetric flow rate assumption is not the same between both. Now we have to consider the changes in density with the temperature and the pressure. So I'm sorry if I've repeated myself so much in this video and so many times, but I really want you to understand this huge difference, because it seems like many people, while they do understand that compressible fluids are different than incompressible fluids, they don't really understand why in terms of math, and it's super important for you to understand this. It's going to really help you. So without further ado, this is enough for this video, and see you in the next video.